Okay, so now today we will continue with the discussion regarding discrete time Fourier transform. As you may remember, we have seen two examples of exponentials, decaying exponentials. One of them was a half decaying exponential, a to the n u of n, and the other one was a to the absolute value of n when a is less than 1 in magnitude, which is two-sided decaying exponential. And we have seen the results of those things. Now today we will start with, again, examples. The first example that we will see is a rectangular pulse, like the pulse that we have seen in continuous time. X of n is equal to, by the way, there was an unmuted student. So let me mute that one too. Okay, because there's a background noise. Okay. Now, x of n is equal to 1 within the width of the rectangular window. Let's say it is from minus capital N1 to plus capital N1, something like that. And 0, of course, elsewhere. Now, what is the discrete time Fourier transform of this? If you want to plot this, it would appear to be something like this, maybe, just as an illustration. Like from minus 5 to plus 5, for instance, it is all ones, and afterwards it becomes 0 and stays to be 0 like this on the n-axis. So this is the rectangular pulse of interest. The discrete time Fourier transform expression for this in terms of the formula is quite simple. From minus n1 to plus n1, it's equal to 1 within this range. Out of this range, it is equal to 0. The signal is equal to 0. Therefore, the summation can be limited only into here, where it is 1 times e to the minus j omega n. So it is this finite harmonic summation. But once we write this, combining this into a simplified form will be a little bit difficult. It's a finite series sum, some sort of. And when you simplify it, it becomes like this. It's surprisingly small, as you see. And it's usually given in the table. So you will also be accompanied by this solution during the final examination. In the list of typical transform pairs, this is a typical discrete time Fourier transform for a typical discrete time signal. So you will have it, but N1 will change, of course. And it may be shifted, it will be shifted sometimes. So you may have shifted pulses. So you will apply the necessary properties that we will see on this solution. But it is also interesting to analyze a little bit this solution and what it tells us. It doesn't look like a sinc, first of all, because sinc is sine omega over omega kind of thing, as we all know. So this is not that way, but it is somehow resembling a sinc shape only inside a period of 2 pi, because we know that the discrete time Fourier transforms of discrete time signals must be 2 pi periodic. So this one is also 2 pi periodic, Can we see that it is 2 pi periodic? Yeah, in a sense, we do. In the denominator, we have sine omega over 2. So that denominator part is by itself 2 pi periodic. Okay, we can keep it in mind. So we are like multiplying with 1 over sine omega over 2, which is a 2 pi periodic thing. How about the numerator? The numerator has sine omega times n1, and n1 must be an integer. That's also what makes the numerator also 2 pi periodic. You may be uncomfortable with plus 1 over 2 in the multiplication factor, but that plus 1 over 2 will contribute as sine omega over 2 kind of thing. And that is also automatically 2 pi periodic. So the whole thing, there's no worries. It's certainly 2 pi periodic. So you cannot have a sinc shape which is at the same time 2 pi periodic. So what is this then? Or what does it look like? The shape here actually looks like something like this. I will try to illustrate. It's like a sinc shape until some point, until here, for instance. Almost a sinc shape. It's not exactly, but it looks that way. And then this point here is corresponding to pi. And this is, of course, minus pi. And then from there on, this whole bunch of graph that you see repeats itself. So it starts increasing again to another sinc shape and then decreases back. And then increases again to another sinc shape, etc. So here, what you have is a 2 pi. So this sinc-like pulse, it's a small wave, you can think of it, a part of a wave, repeats itself. This repetition makes everything to be 2 pi periodic. But within this range, from here to here, it seems like a sinc shape. Okay, so this is the result and the visualization of the result. Now, an extension of this example could be considered as x of n is equal to delta of n. Of course, we are able to find this only by using the formula, and from the formula you will find it to be x of e to the j omega to be a summation from 0 to 0. So the summation will only have one component because delta n is non-zero only when n is equal to 0. And over there it is e to the minus j omega n. And in this summation, n is equal to 0. So e to the j or minus j omega n is e to the 0, which is also 1. So the discrete time Fourier transform is 1. Quite similar to the continuous time Fourier transform of an impulse. But is this 2 pi periodic? Could be a question. And the answer is, of course, it's constant. So it is periodic with anything that you can define, including 2 pi. Because it's just constant. Furthermore, can we relate this to this result? Are they relatable in some sort? And the answer is surprisingly yes. When you take a look at the top, you notice that the sinc-like shape sine omega n1 plus 1 over 2 divided by sine omega over 2. If you take n1 is equal to 0, because it is from 0 to 0 as we see. If n1 is equal to 0, the numerator becomes sine omega in parentheses 1 over 2, 0 plus 1 over 2, divided by sine omega over 2. So it is sine omega over 2 over sine omega over 2, where sine omega over 2 and sine omega over 2 may cancel one another and you will get 1. A problematic region, you can think, is when omega is equal to 0. And when omega is equal to 0, it becomes sine 0 over sine 0. And well, they are identical. The numerator and the denominator are identical. So in the limiting case, that 0 over 0 will boil down to become 1. Okay, that the numerator and the denominator are 0. We know that sine omega divided by omega as omega goes to 0 is also equal to 1. But sine omega over sine omega is quite naturally easier than that. It becomes 1. So it's 1 everywhere. Impulses, discrete time Fourier transform is just uniform ones. Now let us continue with another example. And this example somehow gives us a way to understand the discrete time Fourier transform of periodic signals. Because we know that if you have a periodic signal, periodic discrete time signal or continuous time signal, what we have are called the Fourier series, not the Fourier transform, okay? And if you try to find the Fourier transform directly from the formula, you will fall into a trap of trying to find the summations or integrations of infinite extent and repeating sequences which do not easily converge. So they are very difficult, they are very problematic. So what were we doing? Do you remember what we were doing in finding the Fourier transform of continuous time periodic signals? We were finding the Fourier series coefficients of that periodic signal, and we were inserting impulses into the positions of the Fourier series coefficient harmonic frequencies. And the impulses were 2 pi times the Fourier series coefficient. Simple. As a matter of fact, the situation is very much the same here. So if you come up with, for instance, a periodic signal like this, x of n is equal to e to the j omega 0 n. So omega 0 is the frequency of the periodic signal x of n. It is like 2 pi over capital N. Okay? And capital N is the period of that periodic signal. So what is the Fourier transform then? The Fourier transform is, I may try to write it in words. The Fourier transform is obtained by 2 pi times AK. The AKs are the Fourier series coefficients, and we multiply them by 2 pi, and that's the impulse value. Impulse value. Where's the impulse? The impulse is at the corresponding harmonic frequency. Now, what is the Fourier series coefficient, or what are the Fourier series coefficients of this x of n? The Fourier series coefficients need to be found of this discrete time signal. Now, this discrete time signal only has one harmonic. Sometimes people or students get confused when they see this kind of an expression. They tend to write down the Fourier series coefficient formula and put it inside this, because it's already in the form of a complex exponential. You don't need to do that. If it is in the sinusoidal form, you don't need to do that either. You first convert it into this complex exponential format using the Euler's formula, and then look at the coefficients which multiply these. It is already in the complex exponential form. Since it is too easy, Sometimes students get confused. What am I gonna do? Let me put it in the formula and find the Fourier series coefficient. No, it is the harmonic itself. And you see, what is the coefficient of this harmonic? The coefficient is 1. It is 1 times e to the j omega 0 n. Therefore, the Fourier series coefficient is 1. What is k? K is equal to 1. And what is the frequency? Omega is equal to 1 times omega 0, which is omega 0. So at omega 0, we have one coefficient whose value is 1. So let's put it on the, this is also behaving interestingly. It may be a memory issue somehow. Now that I am screen sharing and things like that, there must be a leakage. So it's like the situation is like an impulse at omega is equal to omega 0. Let's say that omega 0 is here. And this is the frequency axis. And I'm plotting x of e to the j omega. And the impulse magnitude is 2 pi times 1. So it is 2 pi. This is the impulse that we insert. Are we finished? We are almost finished. It is almost, because we found only one of the impulses, and it seems to be the only impulse, by the way, because it's the only Fourier series coefficient. But remember that the Fourier series coefficients were periodic with a period of capital N. So capital N after this A1, instead of A1 at A sub capital N plus 1, there is another Fourier series coefficient. At A sub 2 capital N plus 1, there is another, etc. So we have actually a lot more. Oops, oh, it erases just everything. I'm sorry about that. So I was trying to draw something longer. So the situation is more like this one. We have one impulse for omega 0. We need to put one other impulse for n, capital N plus 1. But what does it correspond to in frequency? Where is it in terms of the frequency? In terms of the frequency, it appears at, so for instance, if this is 2 pi, okay, I'm just putting some arbitrary place. The next one appears at 2 pi plus omega 0. So the place here is 2 pi plus omega 0. It's again with the same magnitude. And then we have 4 pi, and therefore we have another repetition here, 4 pi plus omega 0 with the same magnitude and with the same magnitude, etc. It goes on like this. I don't know if I'm drawing correctly. No, the last one is incorrect. The location-wise, it must be. Ah, yeah, it was correct actually. Why did I remove it? It goes on like this. If you are uncomfortable with this kind of a visualization, you may think of it like this. We found one of the coefficients at the desired place, and all the other ones are artificially kind of inserted or generated to make this capital X of e to the j omega 2 pi periodic. So the whole thing here is 2 pi periodic, which must be 2 pi periodic. So we make it to be 2 pi periodic. So the original distinct capital N discrete time Fourier series coefficients are, you can think of it like between 0 and 2 pi, or they are between minus pi and pi, you find them, you insert them, you make them first as impulses, and then you start repeating them to make everything to become 2 pi periodic. That's the methodology that you may apply. So our observation is put 2 pi times ak impulses at omega k for n Fourier series coefficients. Let's say between 0 to 2 pi or minus pi to pi. Then repeat them to make x of e to the j omega 2 pi periodic. Okay. 2 pi over capital N will correspond to omega 0. Twice of that will correspond to 2 omega 0. Minus 1 times that one, which is minus omega 0, would correspond to a minus 1, etc. So that's how you are going to render the Fourier transform, the discrete time Fourier transform of a discrete time periodic signal. Let's see 2 more trivial examples of this one. The first example is a sinusoid, which is almost in the form of complex exponentials, as we know, because it's easy to expand these into Euler's expansion. We know that using that expansion, this is equal to 1 over 2 e to the j omega 0 n plus 1 over 2 e to the minus j omega 0 n, which means a1 is equal to a minus 1 is equal to 1 over 2. Okay, there are 2 harmonics, 2 Fourier series coefficients, and it may be nice, since this is an example, it may be nice to give a value to this omega 0 thing. Omega 0, let's say, is equal to 2 pi over 5. So the period is 5, okay? Without this knowledge, it's not easy to draw just something arbitrarily generic. But it's still fine. By the way, at the top one, I seem to have forgotten to give the overall formula in an analytical form. So what is x of e to the j omega? How can we write down the mathematical expression of that? As you see, there are infinitely many impulses, so it's an impulse train. So it is, and the magnitudes are all 2 pi, so I can write it like 2 pi summation of infinitely many impulses from L, from minus infinity, let's say, to plus infinity, delta omega minus omega 0, which is an impulse at omega 0, and 2 pi periodic versions of that, minus 2 pi L. I'm unable to close the parentheses here. Sorry about that. I hope you can see that. It's 2 pi times infinite summation of impulses of delta omega minus omega 0 minus 2 pi L. Okay, that is the correct way of writing these. If omega 0 is 0, that would be delta omega minus 2 pi L, which would correspond to an impulse train starting from 0, and the next one is at 2 pi, the next one is at 4 pi, etc. It would go on like that. Now, this one, how can I express? We have 2 exponential terms like that. First, let's try to visualize it graphically, like this. So we have 2 impulses at omega 0 and minus omega 0. whose values are 1/2 times 2 pi, which is pi actually. So we have two impulses. Let's write it like this. Their value is pi and pi. One of them is at omega 0, the other one is at minus omega 0. And then there is somewhere like here, there's a 2 pi. Around 2 pi, we have again two impulses like this. And then we will have a 4 pi, let's say somewhere here. And around this 4 pi, we have two more impulses. So we have the impulse pairs, okay, two impulses, and they are repeating themselves with a period of 2 pi to the left and to the right, of course, on the frequency axis. And this is the visualization of x of e to the j omega. Now, this, how can we write this? I didn't pay much attention to whether the period was 5 or omega 0 is 2 pi over 5 or anything like that. Sorry about that, although I said it here. The shape does not really change. So how can we find an expression of this? Let's use this 2 pi over 5 business here. X of e to the j omega consists of two separate impulse train summations. The first one is pi times, let's say, again, let's use L from minus infinity to infinity, delta omega minus, omega 0 is 2 pi over 5, right? Minus 2 pi L. These are the impulses starting from omega 0, and then the next one is 2 pi plus omega 0. The next one is at 4 pi plus omega 0, etc. And then I have another set of impulses from minus infinity to infinity, delta omega plus 2 pi over 5, because it's at minus pi over 5. It was at minus omega 0. So the next one is 2 pi minus omega 0. The next one is 4 pi minus omega 0. The next one is 6 pi minus omega 0, etc. Like this. So you should write it like this and maybe put it inside a box to indicate that this is the answer to our question. Let's give some impressions about what kind of gradings you may have if you give some vague answers, like if you only say that there is an impulse at omega 0 and minus omega 0, these two impulses, will it be a correct answer? Unfortunately, no. And this time you will not get any partial credit from that if you say it like that. Because it means that you have forgotten a fundamental concept of discrete time Fourier transform. And that fundamental concept is the Fourier transform of discrete time signals must be 2 pi periodic. You give me only two impulses, or you write down an expression corresponding to only two impulses, which is violating everything very fundamental for the discrete time Fourier transform, the 2 pi periodicity. Where is it? So it would be a major mistake, and you will get nothing out of this question if you make that kind of a mistake. Okay, so be careful about that. Don't forget to extend it to become 2 pi periodic. Right, and the next example is another typical example of a discrete time periodic signal. This time, the signal itself is an impulse train. Like this. This is an impulse train, and it's naturally periodic with capital N because we insert impulses, discrete time impulses, samples. So what are the Fourier series coefficients? What were the Fourier series coefficients? You may go back and check them from your notes, from your tables that will be available to you as copy sheets during the final examination. And it's equal to, the AKs were equal to all 1 over capital N. So impulse train Fourier series coefficients were constant. They were not decreasing. They were all equal to 1 over capital N. So what is the Fourier transform then? You have to think of or associate the Fourier series coefficient value with the corresponding frequencies. And I'm telling you that for all the harmonics, AK is this, 1 over capital N. So what are the frequencies? The frequencies are for all k times omega 0, or for all k times 2 pi over capital N. So at the position of omega 0 is 2 pi over capital N because the period is capital N. For all integer multiples of 2 pi over capital N, we have the same Fourier series coefficient. So let's first visualize the situation. I am trying to draw x of e to the j omega. Where is the first Fourier series coefficient? For k is equal to 0, right? When k is equal to 0, frequency is k times omega 0, which is 0 times omega 0, which is 0. The frequency is 0. The Fourier series coefficient is 1 over capital N. 2 pi times that is 2 pi over capital N. So let's write it like this, 2 pi over capital N. An impulse here at 0. Where is the next Fourier series coefficient? The next Fourier series coefficient is at 2 pi over capital N with the same magnitude. The next one is at 4 pi over capital N. The next one is at 6 pi over capital N. It goes on like this. Until where? Until indefinitely. Actually, there's also another one at minus 2 pi over capital N, minus 4 pi over capital N. And it also goes on to the left-hand side with the same way. Now, look at this expression or these impulses and make sure that they are 2 pi periodic. But this time I can see that they are already 2 pi periodic. If something is 2 pi over an integer periodic, it automatically becomes 2 pi periodic. For example, let's say that capital N is equal to 5. Okay, then at 2 pi over 5 we have an impulse. At 4 pi over 5 we have another impulse. At sorry, this is 6 pi. At 6 pi over 5 we have an impulse. The next one is at 8 pi over 5. And here I have another impulse at 10 pi over 5. What is 10 pi over 5? It's equal to 2 pi. And from there on, it goes on. So if anything is, if any x of e to the j omega is 2 pi over n periodic, then it is also 2 pi periodic. So you don't need to try to deliberately or explicitly replicate everything to make it 2 pi periodic. These impulses are already rendering a 2 pi periodic signal, a 2 pi periodic frequency signal, some signal in the Fourier domain. So how can I write it in an analytical form, mathematical expression of this? It's equal to 2 pi over capital N summation infinite impulses. Let's say k from minus infinity to infinity delta omega minus simply 2 pi over capital N or omega 0 times k. as simple as this. This summation will automatically give you the Fourier transform expression, and it is naturally 2 pi periodic because capital N is an integer number. Okay. So it's 36 minutes. I will start. I don't know. Oh yeah, it automatically continues the page numberings. I wasn't sure about how the new pages are generated in this new application. I will now start listing the properties of the discrete time Fourier transform with which, like we have done before, we will solve questions. Discrete time Fourier transform properties. And I have to indicate that these are similar to discrete time Fourier series properties that can be found in the book. And but this one is 2 pi periodic. I'm saying it again and again because that's critical. So we can write the property number 1 like x of e to the j omega plus 2 pi is the same as x of e to the j omega. So if you shift or push omega 2 pi to the right or to the left, or integer multiples of 2 pi, you will come up with the same shape. When you draw them, you have to make them 2 pi periodic. Here I want to give you an example of what those shifts may correspond to in time domain. What some shifting in the frequency domain will make in the time domain. It's not like the example to this one, but it's an example in general. Suppose that we have a Fourier transform, let's call it capital X of e to the j omega, like this. It's a low pass signal from minus omega c to omega c. And let's say this is pi, this position is pi, and we have around 2 pi, therefore it repeats. And here it repeats again, like this, like this. So this is a low pass signal. And it corresponds to a time domain signal, x of n. Let us shift, let's shift x of e to the j omega by pi to make y of e to the j omega like this, to be equal to x of e to the j omega minus pi. I shifted this x of e to the j omega by pi. It may be to the right or to the left, actually. It doesn't matter for this example because pi is just the middle of 0 and 2 pi. But I'm shifting to the right hand side for this one. And I will get a new signals Fourier transform, which is y of e to the j omega. And around pi, it will be like this, okay? And around minus pi, it will be like this. And the others will be also repeating with a period of 2 pi. So where is 2 pi? 2 pi is here. So everything repeats itself with respect to 2 pi, and I will have this time this and this. etc. So this is, as you see, a low pass signal from minus pi to pi. In between, I have from minus omega c to omega c, whereas this one is a high pass signal because I am cutting from minus pi to pi. If you look at it, the signal is in the corners, on the edges of pi and minus pi. And pi and minus pi are, as we all know, the highest frequencies that we have. So this is a high pass signal. By shifting in the frequency domain, I obtained a high pass signal. What is happening in the time domain? We have this one corresponding to x of n, and this one corresponding to y of n. And if you make this kind of a shift, it will be, maybe it may be a future property, but we are not going to cover that property. This example already shows you that property. If you shift in frequency, you multiply in time domain with the corresponding complex exponential. Y of n is essentially e to the j pi n times x of n. Okay, this is the relation between the time domain signals. You shift by pi, so you multiply by e to the j pi n. Okay, that is the property you can think of. That was a property in discrete time Fourier series, so you may check the properties from there. Or if you just briefly take a look at the properties from the Oppenheim's book regarding this chapter of discrete time Fourier transform, you will also notice and see this property. These properties will also be provided to you in the form of tables during the examination. So you will not be confused about how to apply the property. The critical thing here is e to the j pi n, which is the result of shifting by pi in the frequency domain, is an easy signal, because e to the j pi is an easy signal. What is e to the j pi? Do you remember this? E to the j 2 pi is 1, by the way. And e to the j pi is minus 1. In fact, e to the j 2 pi is e to the j pi square, which is minus 1 square, and that's what it makes, it plus 1. So this e to the j pi is equal to minus 1. It's a Euler's identity. And therefore, this is equal to minus 1 to the power n times x of n. What was minus 1 to the power n? It is 1 for n is equal to 0 or 2 or 4, or for all even n numbers, it is equal to 1. And for all odd values of n, it is minus 1. So minus 1 to the power n is 1 minus 1, 1 minus 1, 1 minus 1, etc. It's an alternation, sign alternation. Suppose that x of n is a smooth, continuous time, discrete time signal. It is discrete time, but it is low pass, so its oscillations are relatively less, okay, some smooth variations. This is x of n. Then y of n, from here, y of n becomes alternating in signs. For even numbers of n, for n is equal to 0 or 2 or 4 or minus 2, minus 4, etc., it will stay. But for all odd valued indices of 1, 3, 5, minus 1, minus 7, etc., it will be multiplied by minus 1. So I'm going to keep the value at 0. I'm going to keep the value at minus 2. But at -1, I'm going to make it negative, like this. At 1, I'm going to make it negative, something like this, perhaps. I'm going to keep the value at 2. I'm going to make it negative at 3, and then have the same as it at 4. 5 is negated, 6 is the same, 7 is negated, 8 is the same, sorry, and 9 is negated. Now this is low pass because it's not having a lot of value oscillations or variations, whereas this is quite high pass because it's positive, negative, positive, negative, positive, negative. It has an envelope which is similar to x of n. This is y of n. The envelope of y of n is similar to that, but it's making oscillations, positive and negative oscillations, making it artificially, in a sense, extremely high frequency. That's why we have a harmonic at pi. Whenever you see some positive, negative, or positive zero, or negative zero, negative zero, that kind of oscillations with period equals 2, period is equal to 2 means you have some content at pi. That's why the Fourier transform actually looks like this, the top shape. Okay, so this is one property that we have seen, and it also explains the situation of how the Fourier transform shapes appear on the frequency axis. They are always 2 pi periodic. When you shift them, all of the 2 pi periodic things are altogether. Okay, be careful about these. Okay, now before proceeding with the other properties, we will see 1, 2, 3, maybe 4 properties, 4 more properties with examples. Excuse me for the interruption, but it was just the time. I was trying to give a break anyway. We will meet at 10:05 at the same place. Until then, we give a break of about 15 minutes. At the same place, we will meet again at 10:05. Okay, so let's give a break now. I will stop the recording and I will go out. We will meet again at 10:05. If you have any questions, you may collect those questions in your minds and you can ask me after the break. So until then, see you. Bye-bye.